So in this lecture, we're going to talk about temperature and kinetic theory. So we've done classical mechanics, we've done fluid motion, now we're moving into thermodynamics. And I will say that this PowerPoint has a lot of derivations, but I think it's worth it. So, as you're probably well aware, there are many different types of matter, right? And we've kind of talked about this already, right? We have solids, we have liquids, and we have gases. But on a microscopic scale, the arrangements of the molecule in these different types of matter are very, very different from each other. So what happens whenever we add thermal energy to these different types of matter, right? So thermal energy is related to the microscopic motion of atoms around their equilibrium position. So we can kind of think of this as like the bonds between atoms as being springs, right? So you see this with my little jiffy here, right? So if I add thermal energy, right? Thermal energy is a type of energy. We've talked about kinetic energy, we've talked about potential energy, now we're going to talk about thermal. So if I add thermal energy to a system, like this would be a solid where the bonds look like these little springs, it increases the motion of the atoms, right? So thermal energy gets converted into kinetic energy. And the greater the motion, the greater the kinetic energy. The more kinetic energy that these molecules have, the further away from equilibrium they move, so that turns into potential energy of a spring. So in an isolated system, energy cannot be created or destroyed, but it can be transformed. And this is a great example of the transformation of energy, right? Thermal energy, we are heating something up, we're transferring thermal energy there. This turns into kinetic energy, which causes the atoms to move away from equilibrium, right? They now have a velocity, which increases the potential energy, and this turns into like an oscillation or a vibration of the system. So heat was turned into kinetic energy in this situation. And this leads us to temperature, heat, and the laws of thermodynamics. So, the 0th law of thermodynamics, it's not the first because it was actually found after all the others, so it still needs to be in front though. So they call it the 0th law of thermodynamics, and this basically just tells us that if we have an object A and an object B, and they are separately in thermal equilibrium with object C, meaning A and C are in thermal equilibrium, and C and B are in thermal equilibrium, then A and B also have to be in thermal equilibrium with each other. And this is a law that makes it possible for us to define what temperature is, right? Objects that are in thermal equilibrium with each other are at the same temperature. So basically what this says is that if objects A and B are separately the same temperature as object C, then A and B also have to be the same temperature. So what is the difference between temperature and heat? Sometimes colloquially we use these interchangeably, but they're not the same thing. So temperature, we use the letter T as our variable, and heat we use the letter Q as our variable. Temperature has units of Kelvin, while heat has units of joules. And if you recall, joules was also the unit that we used for energy. So that tells us that heat has to be related to energy. So heat is our transfer of thermal energy between substances, right? If we're heating something up, we are transferring thermal energy from one object to another, right? From a fire to a pot, from my hand to the mouse, computer mouse, we are transferring thermal energy. Temperature, on the other hand, is a measure of the average kinetic energy of the molecules of a substance. So heat is a energy transfer, thermal energy transfer between substances, and the temperature of something is dependent upon the kinetic energy of that something. So we use the triple point of water to define the Kelvin scale, and this triple point of water occurs at 273.16, I think it should be 15. Kelvin, right? And our triple point is a single temperature and pressure where liquid, vapor, and solid can coexist in equilibrium with each other. So it's a very specific temperature. So what happens whenever we heat a solid up, right? Whenever we transfer thermal energy to a solid. Well, when you heat up a material, tends to expand, and when you cool it down, it contracts. Why does this happen? Well, if an atom is pulled away from an equilibrium position, the bond provides that restoring force, right? Like a spring. At ordinary temperatures, we can see that these atoms vibrate around their equilibrium positions very, very little. But as we increase the temperature, we increase the kinetic energy, right? The potential energy also ends up increasing, and this thing starts to expand out, right? The atoms are moving further and further away from the equilibrium position, so this object continues to expand out and out and out and out and out. So the whole solid expands. And we can measure that expansion with this equation here. And this is one-dimensional expansion. So this is just looking at like the length for an example. So the change in length of an object is equal to alpha, so our coefficient of linear expansion. This is not angular acceleration. We are in a different type of physics, so our variables are changing. Well, it's the same letter, it's representing something different, right? So alpha is now our coefficient of linear expansion. L0, sometimes people call this L naught. This is the original length of the object, and then delta T is our change in temperature. So we can also have 2D expansion, right, area expansion, or 3D expansion, which is volume expansion. And these equations follow like the same structure. What changes is going to be our coefficient. So what happens if we have like this strip here that has two different materials and they have two different coefficients of expansion? Well, they're going to expand and contract at different rates. So you see that the brass contracts more and expands more, right? So it is more responsive to changes in temperature than steel, for example. And the coefficients of expansion are things that are experimentally determined. So there will be a table in your textbook that holds the coefficient of expansion for different materials. So one thing that's interesting is if we move from a solid and we move into liquids, we can think about something like water. So water behaves differently from most other solids. So when I'm talking about water as a solid, I'm just talking about like ice, right? So water's minimum volume occurs when the temperature is 4 degrees Celsius. If it cools any further than that, it starts to expand out, and if it warms up, it starts to expand out. So what's really interesting about water is the fact that like most objects, if you cool them down, they will continue to get smaller and smaller and smaller and smaller and smaller. Water does not do that, right? And that's why whenever you have a water bottle in your car in the winter and it freezes, it will explode. Because at 4 degrees Celsius, this is going to be the most constriction that occurs with the water molecules. Anything above or below that is going to result in expansion. So, fantastic. We talked about solids, and we've already talked about liquids quite a bit, right, whenever we're talking about fluid motion. So, what about gases? Well, if we want to think about what happens to a gas whenever we have heat transfer or whenever the temperature changes, generally we think about this through the ideal gas law. And if you've had chemistry classes, you are probably very, very familiar with Pivnert, right? So, the ideal gas law tells us that pressure times volume is equal to nRT. So N, in this situation, is going to be our number of moles, R is going to be our gas constant, and T is going to be our temperature. And this is the one that you're probably most familiar working with. But this is a macroscopic view, and everything I've been talking about is microscopic. So when we move to the microscopic, we still have PV, and we still have a T, but our lowercase n changed to a capital N. And this capital N represents the number of particles, not the number of moles. And then we have this Boltzmann constant. And this Boltzmann constant is just our gas constant divided by Avogadro's number, right? So if we're looking at microscopic changes, we use the equation that involves the Boltzmann constant and the number of particles, where if we're looking at macroscopic changes, we use moles and we use the gas constant. Now, which one you use is really determined by the problem, right? If we're looking at something macroscopically, or if it gives me the number of moles, generally I'm going to use the PV equals nRT. If I am looking at something microscopically, or I'm given like the number of particles, I'm going to use PV equals in Boltzmann constant T. Also, your field of study can dictate which one of these equations you want to use. So, microscopic view of pressure. What actually causes pressure? Well, if we look at a box, and this box contains a bunch of particles in it, the particles have some potential energy, and this potential energy is related to their positions relative to each other. Remember that potential energy is not just restricted to like a ball and the ground, or the distance of something from ground level. Potential energy is energy that is related to the positions of objects relative to each other. So, all of these particles have potential energy. They also have kinetic energy, right? Because they're moving and bouncing around. So as these molecules bounce around and they have kinetic energy and their velocities are changing, they come into collisions with the wall, right? So we have, on the most basic level, an elastic collision between the particle and the wall, right? And this collision between particles and the wall or this box is what actually is causing pressure. So, interestingly enough, particles, as they bounce off each other, they move around, they follow something called Brownian motion, right? So a gas molecule is going to move in straight lines in between its collisions. This is also something called a random walk. There's a lot of really interesting physics involving random walks, and I do encourage you to explore that a little bit. I think it's really fun. It's interesting stuff, but we'll move on. So, what happens, and what is the relationship between pressure and volume and temperature, right? So, if I have this box and it's full of particles and they have some velocities, if I increase the temperature of the box, I'm going to increase the kinetic energy of the particles, meaning that the particles are going to make more collisions with the wall, or these collisions are going to be more frequent, and they'll do this with a greater force, so this increases the pressure. So increasing the temperature while maintaining a constant volume is going to increase the pressure, because these particles are going to continue to bounce around off the walls and they're going to hit harder. Well, what happens if I make the volume smaller but I don't change the temperature? Essentially the same thing, right? So if I make the volume of this container smaller but the temperature remains the same, there's less distance for these particles to travel across the box, so they're still going to make more frequent collisions with the walls of the box and thus increase pressure within the container. And increasing the number of particles obviously means the box will experience more frequent collisions, and this will also increase the pressure in the container. And these are all relationships that we can see with the ideal gas law. So, if we want to take this and we want to understand the microscopic view of an ideal gas, we want to consider something called the kinetic theory of gases. And remember all those conservation laws and descriptions of kinetic energy that we've done a few different times? Well, we're going to do the exact same thing, but we're going to do this with a different topic. And the topic is going to be, obviously, gases. So, in order to do this derivation, we have to make a couple assumptions, just like we had to do for ideal fluids. Remember, with ideal fluids, we made assumptions like it's incompressible, it has streamlined flow, things like this. We're going to do the same thing, but with gases, right? So the first assumption that we need to make is that the number of molecules in the gas is large, and the average separation between them is large compared to their dimensions. Basically, what we're saying is we have a bunch of molecules in this box because we want to use statistics to look at this. So we need to have enough of a number of molecules so that we can have statistically significant results, right? So because the number of molecules is large, we can analyze their behavior statistically. And this is a whole field of study. It's called statistical physics. It's very interesting. If you go to grad school for like chemistry, you're going to have to take statistical physics. So this large separation between the molecules means that our molecules are going to occupy a negligible amount of volume in the container. So we also have to assume that all of these molecules obey Newton's laws of motion, but they move randomly. So they have random motion, they have this Brownian motion, and also they obey Newton's laws. Basically, we're saying that there's no quantum mechanical effects that can occur here. And by randomly, we mean that any molecule can move in any direction with equal probability over a wide distribution of speeds. Assumption 3, we want to assume that the molecules interact only through short-range forces during elastic collisions. So we are assuming that there are no long-range forces occurring. Long-range forces being something like we are ignoring any possible van der Waals force that could be happening here. And we do assume that these are elastic collisions and that the kinetic energy is going to be conserved. The molecules make elastic collisions, right? So we assume that these are hard spheres, so they can't like stick to the wall, and the collisions are frictionless. We want no loss of energy during this process. And we also have to assume that they're all identical, right? So they're all the exact same atom, one type of atom. There's no molecular gases here, right? This is just a monatomic ideal gas. So let's say that we have a box, and in this box I have one single, I have a bunch of particles, but I'm going to track one single particle. And this particle is going to move from one side of the box to the other, bounce off, and move back. So I can represent pressure as our force divided by area, right? How much force is applied over what area? So what force does this collision, does this particle have? Well, it's a collision, so I can make the statement that force is equal to a change in momentum over a change in time. And then our change in momentum is just equal to mass times a change in velocity, right? So our force is strictly due to this change in velocity over a change in time. Additionally, my initial velocity and my final velocity are going to be equal and opposite. Why? Because my kinetic energy is conserved in this scenario. So this means that my change in momentum is just going to be 2 times the mass times the velocity of this object. So force is equal to 2 times mass times velocity divided by a change in time. So how long is it going to take for my particle to move from one side of the container to the other and back again? Well, we know that our velocity is a change in position over a change in time, and my change in position is going to be 2L, right? I'm going to go L length across and L length back. So my time is equal to a change in position divided by velocity, and my change in position is 2L, right? I'm going over and I'm coming back. So I can represent my change in time as 2L divided by velocity. So if I combine these equations together, right, system of equations, plug one into the other, I get that my force is equal to mass velocity squared divided by length. But that's only for one particle. I only tracked the motion of one particle in the system, and in my statement, I said that I have to have a very large number of particles. So if we have n number of particles, we can't track every single particle's velocity, but we can take an average, and that's the whole point of statistical physics, to take an average to simplify things. So the average velocity squared is going to be the summation of the velocities divided by the number of particles, right? So I can rearrange this, and I can replace my v squared, right? This is my v squared in my force equation with the average force for n number of particles is equal to n, which is my number of particles, times the mass times the average velocity squared divided by length. So this is my new equation. But we have another issue. I only considered one dimension, and in real life, things are three-dimensional. So the calculation that I did, this equation that I came up with, is only for the x direction. I need an equation that represents the x, y, and z direction. Well, for simplicity, we assume that the box is cubic, so this means that the average velocity squared is equal to the x portion squared plus the y portion squared plus the z portion squared, right? This is just vectors. I'm turning it into a vector. So if this box is cubic, then x is equal to y is equal to z. So my velocity squared is just equal to 3 times the average velocity in the x direction squared, or I can replace this average velocity in the x direction squared with 1/3 velocity average squared. Great. Now we have an equation that represents the force. Remember that we're trying to get pressure is equal to force divided by area. That's where we're at. I now have an equation for the force for n number of particles, and that is equal to the number of particles times the mass times the average velocity squared divided by 3 times the length. So we can state that volume is equal to area times length, and when I plug my force in up here, my A comes down to the bottom and I have A times L. So this, I can replace this with volume. So I put little serifs on my volume so that hopefully you could differentiate it from average velocity. Now we're going to do a math trick. You should not automatically say to yourself, oh, I think we should do a math trick. This is something that, in all honesty, somebody teaches you and then you teach somebody else and then they teach the next person, and it's passed down like we are a storytelling culture of physicists. So we can actually apply a math trick, right? We can multiply times 2 divided by 2. So this is the same as multiplying times 1, right? And if I multiply the top and the bottom times 2, I get my equation for pressure. So I can pull out 1/2 mv squared, and note that this is kinetic energy. I can pull this out of this equation. If you don't believe me, do the math. So I can represent that whole 1/2 mv squared as kinetic energy. And I'm going to move that v over to the other side, and I get this equation. Pressure times volume is equal to 2/3 times my number of particles times my kinetic energy. Well, I also know that pressure times volume is equal to my number of particles times the Boltzmann constant times temperature, right? My ideal gas law. I can state that 2/3 N times kinetic energy is equal to N Boltzmann constant temperature. Rearrange, and the kinetic energy of one particle, because I got rid of my N's canceled out, so now I only have one particle, is 3/2 Boltzmann constant times temperature, or 3/2 RT. So if I want the internal energy, U is the internal energy of the entire system, I have 3/2 times the number of particles times the Boltzmann constant times temperature, or internal energy is equal to 3/2 nRT. And this is how you arrive at the internal energy equation for a gas that you all use in chemistry.